Hello students, in today's lecture, we are going to discuss the numericals of diffraction grating. So let us first revise all the formulas we will be requiring to solve the numericals. For grating, the intensity spectra equation is given by a square sine square alpha upon alpha square sine square n beta upon sine square beta. Width of nth order principal maxima is 2 lambda upon n into a plus b cos theta n. A plus b is your grating element, lambda is wavelength. Okay. Dispersive power of a grating is given by d theta upon d lambda, which is equal to 1 upon under root a plus b upon n whole square minus lambda square. Direction of spectral lines in a grating are given by a plus b sine theta equal to n lambda. And the grating element is given by the ratio of width of grating divided by total number of lines on the grating. So let us begin with the numericals. Two plane diffraction gratings are having the same width, but A has large number of lines compared to B. Now you have to find the intensity of the fringes. See, formula of intensity is directly proportional to total number of lines on the grating square. So intensity of A is greater than B, but width of nth order maxima is given by 2 lambda upon n into A plus B. So it is inversely proportional to total width of the ruling surface. Since gratings A and B have same width of ruled surface, hence it is the same for A and B. Let us see dispersive power. The formula is d theta by d lambda is equal to this much. Dispersive power is coming inversely proportional to grating element. So grating A has greater number of lines of the same width of ruled surface as B. So it has a smaller grating element, hence large dispersive power compared to B. Next, white light is incident on the grating. What is the value of grating spacing? The second and third order spectra overlap. Okay, direction of spectral lines for grating is a plus b sine theta equal to n lambda. A plus B has been given to you as D. So for second order, n equal to 2, spread between angles alpha 1 and alpha 2, you are getting this much. So you get the value of angle between them as equal to this much quantity. For third order spectra, the spread between the angles has been found out as this much. So from the above relations, you can see that the range from 12 into 10 to the power of minus 7 upon D to 14 into 10 to the power of minus 7 upon D is common in second and third order. Hence, irrespective of the value of D, second and third order spectra overlap. A parallel beam of monochromatic light is allowed to be incident on the grating. You have to find the wavelength. Grating equation is a plus b sine theta equal to n lambda. Grating element is equal to a plus b is 1 upon 1250. Angle given is 30 degrees. Sine 30 degrees half. Order given is 2. So we get lambda as this much. In a plane transmission grating, the angle of diffraction has been given. Calculate the number of lines. Grating equation, a plus b sine theta equal to n lambda. Number of lines in 1 centimeter is equal to 1 upon a plus b. So n equal to 2, theta lambda, you get lambda and 1 upon a plus b value. Calculate the angle between central image and its first diffracted image produced by a fabric with 160 threads per centimeter. Okay. Grating equation you apply, put n equal to 1, lambda 6 into 10 to the power of minus 5. You get the value of sine theta, where you are, that is what you have been asked. Two spectral lines are having wavelength so much. Show that if this is less than this, the angular separation is given by this. See, plane grating element formula is a plus b sine theta equal to n lambda. Now, when you will differentiate this with respect to lambda, you get d by d of sine is cos. So d theta comes out as this much. Sine square theta plus cos square theta is equal to 1. Put this value of sine in the expression for dispersive power of a grating and you directly get the answer. Find the angular separation for so much wavelength in second order spectrum. Dispersive power d theta is equal to d lambda upon under root a plus b by n whole square minus lambda square. Now, since this value is very low, you can neglect it and your formula becomes d theta is equal to n d lambda upon a plus b. And d lambda is difference of this. So a plus b comes out as this much. Just directly put it in the value of d theta and you get the answer. Light of wavelength is incident on a plane transmission grating, angle of diffraction. Simple formula, a plus b sine theta is equal to n lambda. You find out the value of a plus b, put it in the expression for sine theta, and you get your answer. Next, monochromatic light with a helium neon laser is incident on a diffraction grating. Again, the grating equation is a plus b sine theta equal to n lambda. You put the values if theta 1 and theta 2 are the angles at which the first and second order maxima are observed, then theta 1 is this much, theta 2 is this much. Parallel light consists of two monochromatic radiations and this much. What is the angular separation? See, position of principal maxima are a plus b sine theta equal to n lambda. N is equal to 2, lambda 1 is 6 into 10 to the power of minus 35. So your sine theta value or the theta 1 value comes out. Similarly, for the second monochromatic radiation, theta 2 comes out. And angular separation is theta 2 minus theta 1. Diffraction grating is used at normal incidence. It gives a yellow line. So much, calculate the grating element. Principal maxima for normal incidence has been given. Nth order maxima of lambda 1 coincides with n plus 1th order of maximum lambda 2. So your equation becomes this much. Putting this value in the equation, we get the answer. Grating element value you find out. Straight away, 1 angstrom is 10 to the power of minus 10 meter, 10 to the power of minus 8 centimeter, and you get your answer for grating element. Diffraction grating is used at normal incident, gives a green line in a certain order, superimposed. Calculate the value of n and find out how many lines per centimeter are there. Principal maxima is given by this formula. Nth order maxima of this coincides with n plus 1th order of this, then we get this. So the order is 3. Then the grating equation, sine 30 is half. Number of lines per centimeter, 1 upon a plus b. In a grating spectrum, spectral line in fourth order will overlap with third line. Grating equation, a plus b sine theta equal to n lambda. Fourth order will overlap with the third order. So for third order, it is this, and fourth order, it becomes n plus 1. Third order, n equal to 3. Fourth order, n plus 1 equal to 4. Highest order spectrum, which may be seen with light of wavelength by means of grating. Number of orders visible, n into a plus b sine theta upon lambda, n maximize. See, for maximum value, theta is 90, so sine 90 is equal to 1. So a plus b is equal to 1 upon 5,000. So maximum value is coming out as 3. Third order is highest visible order. How many orders will be visible if wavelength of incident radiation is so much angstrom? For grating, a plus b sine theta, maximum value of theta is 90 degrees, sine 90 is 1. Number of orders visible is a plus b by lambda. That's 90. In relation to plane transmission grating, answer the following. What is the largest wavelength of light for which a spectrum can be observed? Wavelength, what is the highest order of spectra? 90% of ruled width of grating is covered. What will happen to observed spectra? Direction of spectral maxima is this much. For longest wavelength, theta must be maximum and n should be minimum. The maximum number of orders visible with grating is